My dear friends, today I am going to explain to you about the fictitious force in a rotating frame and Coriolis force and as well as centrifugal force. Mean how these forces originate, like centrifugal, Coriolis, and fictitious. These are the fictitious forces. So let we start. Now try to understand. This is our red frame. This is fixed, having this is x-axis, y-axis, z-axis, and unit vectors I cap, j cap, k cap. This is fixed, and origin is O. There is another frame, shown with green in color, like x dash, y dash, z dash. This is frame S dash, and this is frame S. And our green frame, the unit vectors are I cap dash, j cap dash, k cap dash. This frame is a rotating frame. It is in rotation. Maybe it is in translatory motion, or maybe it is in acceleration, of course, but one thing is sure, it is a rotating frame. These directions, they are not fixed, they go on changing. I cap dash, j cap dash, and k cap dash, they all unit vectors, they are time dependent because frame itself is rotating. Now the origin is O dash. Now from this origin to this origin at any instant, the position vector is r vector. So here it is any particle represented by a point P. Its position from the rest frame, S frame, is r vector, and the position of the same particle from the rotating frame, origin of the rotating frame, is r dash vector. Now apply the triangle of vector addition. This vector, they are along the same order. That r vector becomes this plus this. So this is our first equation. Now then, writing this position vector r dash, because the position of this particle from this origin can be written in terms of I cap, j cap, I cap dash, j cap dash, k cap dash, because this is dash frame. So instead of r dash vector, it is x dash, I cap dash, y dash, j cap dash, z dash, k cap dash. Now then I differentiated. Differentiating means, when I am differentiating, that means this position from the origin, it is changing. That means this particle, it is in motion. It is in motion because I am differentiating. I am thinking this r is changing with time. This capital R means this frame is also in motion. When it is in motion, r vector will change with time. So r vector is changing with time. And this dash frame, because it is a rotating means it is a function of time. Now because distance over time is velocity, this is r vector from origin O with respect to S. So this velocity is called definitely Vs. dr over dt means velocity of this frame. Velocity means translatory velocity, translation. With respect to this origin, this velocity is V. Mean velocity, linear velocity of the rotating frame from this origin. Now then, x dash and I cap dash both are the function of time. So first of all, first function as it is differentiation of second, differentiation of first, second as it is, like that. And I'm having here two terms for this, two for this, two for this, 1, 2, 3, 4, 5, 6. Okay, so this becomes the result. Now then, note down here what is I cap dash dx dash over dt, j cap dash dy dash by dt, dz dash dt, and k dash. What is dx dash over dt? What is distance over time? Velocity. And it is dash. I mean it is velocity in the rotating frame. Moreover, I cap dash. So this velocity mean this dx dash over dt, dy dash over dt, dz dash over dt, combining these three terms. So it becomes the velocity in the dash frame. Velocity in the dash frame. Mean when you observe the velocity of this particle from here, from this frame, for this space which is rotating, as well as it is in translatory motion. When you observe the velocity of this particle, that will be Vs dash. Okay, when you observe the particle from the S frame, there is a velocity, linear velocity of the rotating frame. When you observe the particle velocity from the rotating frame, now then you are having three terms, this plus this plus this. So written here. Okay, now coming a fact. If a particle is orbiting like this, okay, relation v equals to r omega, relation between linear and angular velocity. I wrote this relation in vector form, nothing else. V vector is omega vector cross r naught vector. Keeping in mind scalar in magnitude, it is v equals to r omega. Is okay. So in vector notation, v vector is omega vector cross r naught vector. Now how you write the v vector? If you are having here r naught vector, you will write this relation like v mean distance over time, d r naught vector over dt. D r naught vector over dt, it is equals to omega vector cross r naught vector. Mean this v vector is d, velocity is distance over time. Mean in a circle, when a particle is orbiting in a circle, this r naught, it keep on changing because it is changing direction at every instant. So I am writing v as d r naught upon dt. Okay, omega vector cross r naught. This relation is applicable for, this is a general relation and applicable for any vector. Here I am having d r naught vector upon dt is equals to omega cross r naught vector. I'm a point of view, this relation here I am writing for r naught, but this relation is true for any vector. So I am changing r naught first of all di cap dash over dt. So right hand side, if I say r naught vector is I cap dash, so here comes instead of r naught omega vector cross I cap dash. If I replace r naught vector by j cap dash, so here comes j cap dash. So similarly, if I replace this r naught vector by k cap dash, here comes k cap dash. So now I am going to replace this value, this value, this value with this value, with this value here, with this value here, substituting these values here. So this relation modifies to this relation becomes like this. Okay, I'm having 1, 2, 3, 4, 5 terms on the right hand side, one term on the left hand side. Now then, this x dash may be written here, okay, may be written here. Similarly, this y dash, maybe it is written here. This z dash may be written here. Okay, then this relation becomes like this. Okay, x dash is transferred here. Okay, this, and this. Now next. Now what is x dash I cap dash? From here omega vector, from these three terms, omega vector is common, omega vector cross common, x dash I cap dash plus y dash j cap dash plus z dash k cap dash. Now this is dash 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 dash. So this is actually r dash, position vector. So here comes r dash. So these three terms, they combined to become the one term. So we are having now three terms. Now Vs vector mean velocity with respect to this frame. Okay, respect to this red frame. This is Vs vector. V vector mean velocity of the rotating frame with respect to the origin, mean translatory velocity. Okay. Now then I am having here Vs dash vector. Vs dash vector may be written as dr dash over dt. Okay. What it is? This is the velocity of this particle with respect to rotating and this frame. It is in translatory motion as well as it is in rotation. With respect to this frame, this space, the velocity of this particle, it is this velocity, Vs dash, or may be written as like this. Okay. Then omega cross r dash. Now a special case. When frame S dash is not in translatory motion. Now we are thinking it is not in translatory motion. Only rotating, and moreover its origin is coinciding with this origin. When O dash is coinciding here, then R vector becomes 0. Meaning if O dash coincide with O, the big R, capital R vector turns to be 0. When O dash coincide with O, this capital R vector turns to be 0. Okay, mean this rotating frame is only rotating, and this space is rotating at here. There are two spaces. One is fixed space. The second space, which is again here, it is only rotating. Okay, that's the point. So when it is shifted to this point, this origin is shifted to this point, then there will be, because capital R is 0, if capital R is 0, R vector and R dash vector, they becomes the same. So R vector and R dash vector, they becomes the same. And second, is velocity, translatory velocity of the rotating frame, translatory motion, velocity, which is dr upon dt. This also turns to be 0, which is denoted by small v. Okay, so small v is also 0. So this small v 0. Okay, and r dash is r. This r dash is r only. So the relation becomes like this: dr over dt, fixed frame, rotating frame, no dash now, omega cross r. Okay. Now this is the velocity of the particle with respect to the rest frame, with respect to the rotating frame, omega cross r. Now this relation is here applicable for r vector, but in general it is applicable for any vector like g vector. If I say this relation has, I'm not writing r vector, instead of capital G vector. So capital G vector, capital G vector. This is true. This is fixed, rotating, and this one. Okay. Now like here, this relation written in general form like this. Okay, and we left the expression at here, last expression. Now, I'm writing the general relation changing G vector. Instead of G vector, I change it with V vector. Okay, so this becomes, instead of G, I write Vs. Instead of G, I write Vs. Instead of G, I write here Vs. G, Vs, G, Vs, G, Vs. So this relation turns to be this relation. Okay, and now I already proved on the last paper, Vs is Vr vector and this. So substituting this Vs here, this Vs here. So the relation with respect to rest frame, Vs substituting here, rotating frame, omega cross this, it is here. Okay. Now open the bracket, dVr over dt and d by dt omega cross r, this one. And here we are having the two terms, this and with this and this. Now what is Vs upon dt? Velocity upon time. Velocity upon time is acceleration. Now particle is accelerating, and this is the acceleration of the particle with respect to the rest frame. This is the acceleration of the particle with respect to the rotating frame. Okay. Now omega is our constant. Omega is, it is assumed that omega is constant. So omega cross, this relation is like this. Omega cross dr over dt. Okay. Then this term, then lastly this term. Now I am having 1, 2, 3, 4 terms on the right hand side. Now here, what is dr over dt? What is dr over dt? This is again in a rotating frame, that is the velocity in the rotating frame. Velocity in the this term and this term, they are the same. If they are the same, it becomes the twice. So now I'm having only three terms. This twice and this. Now multiplying each term by m, mass into acceleration becomes the force. This is the force with respect to the rest frame, with respect to the rotating frame, this force and this force. Now I'm interested the force from the rotating frame. Force on the particle with respect to the rotating frame. This is the force on the particle with respect to the space which was at rest. And then this force here, when this is taken to this side, it becomes negative. This force is taken to this side, becomes negative. This is the fixed frame, and second frame is rotating, and there is a particle which is accelerating. The particle is in acceleration, and when you observe the particle, the force on the particle from the rotating frame, that is the real force. This is the force on the particle, this is the actual force. If there is no rotating frame, only the one frame, only one space which is at rest, and particle is P which is accelerating and having, then there will be a force on the particle. And what is that force? This is Fs. So this is called a real force, or it is called the inertial force. This is the actual force. But when you are observing the same particle from the second frame which is rotating, then you are having the different expression of the force. from the real force, there are two more terms which are subtracting, okay, which are subtracting from the real force. So this is force from the rotating. Now we to learn what is this force. Okay, this is minus 2m omega vector, because this is not the real force. And this, it arises because second frame is rotating. That's why these two forces arises. And because they are not the real, these two forces are called fictitious forces. And the first 2m omega cross Vr vector, it is, this force because the second frame, second space is rotating with angular velocity omega. Okay, and this force arises if, there is Vr also. The particle which is in velocity, particle is in velocity and the space is rotating, then this force is called Coriolis force. This force is called Coriolis force. Coriolis force arises because of the frame is rotating and as well as the particle having some velocity. Okay, and this velocity of the particle when observed in the rotating frame. Now, what is the direction of the force? This force, what is the direction? So direction will be, like a vector, like if you say a vector cross b vector is equals to c vector, then the direction of c vector is always perpendicular to the plane in which a vector and b vector lies. So direction of the Coriolis force will be perpendicular to the plane in which omega vector and Vr vector lies. So this is the velocity of the particle in the rotating frame and angular velocity. This is called Coriolis force. There is one another force, last. This is m omega vector cross r vector. What it is? Actually, if you write in a magnitude, write its magnitude, this is m omega square r. Omega v equals to r omega. Okay, omega equals to v upon r. So this becomes m v square upon r r cancels. So m v square upon r. So m v square over r is centrifugal force. You already know. So m omega vector cross r vector is centrifugal force. This is also fictitious force. It is also arising. It is, originating because the frame is rotating with angular velocity omega. So if frame is not rotating, there will not be any this force due to the angular velocity omega. So this is the expression that, So I'm going to sum up that if you observe the force from the rotating frame, okay, that you're observing a particle. Last conclusion, the particle is experiencing a force. If you observe that force from the rotating frame, it is equals to the force, real force, which the particle experiences with respect to the rest frame, and two terms more, which are originating because of the rotating space. And that's why the two forces are called, fictitious forces. Coriolis force, centrifugal force. Okay, thank you very much. If anything is not clear, please write me in the comments box. And if you want any contact, then my contact number is 9888 169 226. Okay, thank you.